So let me talk about what Project 5 is about. And in a sense, Project 5 comes before Project 4. And let me explain that. So this, of course, is a graph. And what we're interested in here, although I never have talked about it explicitly, is we're interested in properly colored graphs. Or I suppose I should say chromatically colored graphs, which simply means that given that the rule for coloring the vertices of a graph is that no two adjacent vertices have the same color, what is the smallest number of colors? Now I can certainly make this properly colored, and if I give each of these 16 vertices a different color, then I've accomplished that. No two adjacent vertices have the same color. However, that's not the fewest number of colors this particular graph requires. This graph can meet that restriction in as few as 4 colors, as is shown here. And if you have then so that's what's referred to as a chromatically colored graph, a graph colored properly with the fewest number of colors. If I were to do that, combine all the blues together, meaning that if I was to, for example, let me do green, so that'll be a little bit easier. If I was to combine this green with this one over here, so let me throw that aside. Then that edge would combine right there. This edge would come here, and this edge would come here. Okay. So if I did that with all the same colors and I combined all the greens and all the reds and all the blues and all the yellows, and by the way, there are only 4 colors used as just for convenience. Of course, you can have a graph that's complex enough that the chromatic number, the fewest number of colors required, is 2,000, right? But it'd be visually impenetrable. So the 4 color graphs you can create some simple examples of, and that's why in the stuff I've given you predominantly things are either 3 or 4 colors. If I combine all of the same colors together like that, then what I end up with is a complete graph, which is 1, obviously the number of vertices you'd end up with are the number of colors, so in this case you'd end up with 4 vertices, and every vertex would be connected to every other vertex. And that's easily proven. I think we can prove that without getting very technical. Let's say that isn't the case, that there was some 4-color graph, chromatically colored 4-color graph where I combine all the greens and all the blues and all the yellows and all the reds, and it's not a complete graph, meaning that there is no edge between green and yellow. Then that would mean nowhere in the original graph is green connected to yellow. If that's the case, then make all the greens yellow. Now I've got a 3-color graph. Since none of them are adjacent, they can have the same color. So if every chromatically colored graph will be a complete graph when you collapse it down. So the starting point is you have a graph and you need to describe it, and that is what the starting point of P5 is. And so this is just a description of this graph. I'd say that I pick a node, doesn't matter. Note that none of these are labeled with numbers, but I go ahead and pick one and I say, okay, I'll call this vertex 1. I label it, or I I say it's vertex 1, so it ends up having the first entry here, and I give it a color, and then it doesn't matter. All I have to do is just list out these 16 in any order. It doesn't matter. And here they are. All I have to do, I don't have to put numbers next to them by virtue of pointing at this. By virtue of pointing at this one first, that's the first vertex. By virtue of pointing at this one second, that's the second vertex, right? It really doesn't matter the order that I choose them. And then after I've listed them out, then I just have to describe the edges, and that of course is what this is a description of all the edges. And in fact, this description that we see here is this graph here. The graph that you animated in Project 4 is this graph here. This is just a different layout of the same graph. So the challenge then is if I describe a graph using this method, and it doesn't matter what method you use. The reason I chose this method is I think this method is really easy to parse. I mean, that's the sole reason for me choosing this method. I could have chosen to use a dot file or GML or any other standardized graph layout description language, but I just chose this because it's easy to parse. So after you describe a graph, what I want to see is I want to see you be able to turn it into an animation, or be able to describe it in terms of evolving, in this example, from a 4-color complete graph to what you see right now. And where the idea of evolution is, of evolving out, is that your complete graph, in this case, your 4 vertices comprising the complete graph are the progenitors, and all greens emit from that first green, and all yellows emit from that first yellow, and all blues emit from that first blue, and so on and so forth. So the only question remains is, if I'm shown this graph, what are going to be my progenitor nodes? Which 4 vertices, and they each have to be of a different color, are going to comprise that complete graph? And the method that I settled on is the first time you encounter a color in this list, that would be the progenitor. So if I note that for my own notation, I kind of blocked these out in gray, which to me visually for my use elsewhere for this graph, these end up being progenitor nodes, and everything collapses into these 4. It doesn't have to be that way. I can go ahead and grab this, and I just take this and slide it over here, and then this would end up being the progenitor node for the greens, right? It really doesn't matter. You just have to choose 4. And to ensure that the 4 that I choose here are correctly identified here, I just come up with the rule. The first time you see a green, it needs to be this one. The first time you see a blue, it needs to be this one. The first time you see a red, it has to be this one. The first time you see a yellow, it has to be this one. And so to make this effort to describe the evolution, it is far easier if I make these 4 grade vertices the very first 4 listed here. It becomes a lot harder if I do what I had in the B graphs. Let's see, can I bring up the... So the reason these are all listed, all greens, all reds, all blues, all yellows, there's no rhyme or reason for why I did that. I could have scrambled these in whatever order I wanted. I was just looking for an easy way to make sure that the first occurrence of a color wasn't 1, 2, 3, and 4. Right? So I could have done red, 2 blues, then a yellow, then another blue. Right? This was just the stupid easy way for me to create the challenge of that's the first one, that's the second one, but the third progenitor is here and the fourth progenitor is down here. And the challenge this creates is a mapping in that when we look at this information here, we did this project first, and what we did is we identified or labeled the vertices in our graph with numbers, and we had the lowest numbers be the progenitor nodes. So we've got a whole bunch of code written with that assumption. Once you've written a whole bunch of code with that assumption, then when we go to the other thing where we're describing a graph, we have to create a mapping where the first time we encounter a red, that needs to be vertex 1. First time we encounter a blue, that needs to be vertex 2, and so on and so forth for the first 4 vertices. And then that's the complexity in project 5 is part B, where you have to do that mapping. Note that other than identifying, where am I here? Other than identifying which are the progenitor nodes, I provided no restrictions whatsoever. There's a progenitor green, and then there are 4 other greens in this graph. It doesn't matter the order in which the other 4 greens collapse onto that progenitor green. So as far as I'm concerned, it doesn't matter the labels of any of those greens except for that first progenitor green, which has to be somewhere between 1 and 4. I don't know, does that help?
I think so. Are we supposed to be like building the graph in the background?
You're going to have, so what you're going to have to do, let's connect to this. Your first step is to read in that file and build this graph. Not graphically, not as an image, but just the data structure in Python. Once you have the graph, then you have to start collapsing in all the greens on the green progenitor and all the yellows on the yellow progenitor. Because what you have to do is be able to reverse engineer it.
So you need project 4 or you do project 5. Because you're still going to have to build the graph.
Right. So that's the output to project 5 is that project 4 file.
Yeah.
And so to illustrate that, let me bring my progenitor back here. If I'm doing this collapse right here, I guess I need to provide some numbers. Text. Why is it not doing that? Well, I guess I got to go down here. Wrong letter. I probably should have chosen numbers that are a little bit higher. 8, we'll call this 8, we'll call this 12, we'll call this 6. Let's see, I'm short 2 others. All that 7, all that 5. get them all? Note that one there. All right. So what you have to do is you have to programmatically identify basically all the nodes that aren't the progenitor nodes, and you collapse them in. So you have node 6. You say, okay, that has to collapse into the green progenitor, which is this one. So that means that this is going to come in, this is going to come in, and that's going to come in. Now, let's stop that. So now you bring that in, and what you note is that 6 and 1 share 12. So the evolution command would be in order or the line that you put in that evolution file would be that 1 is the progenitor, 6 is the progeny, and that 12 is copied, right? Because that's coming right here. That's a copy of 12. And then what is this one? It's a move. It's a move of 7. And then this one is a move of 8. And so you get that done with part A, where all the numbering's nice and easy for you. The progenitors are all the earliest numbers. And then once you get that completely working, then you have to go back and do it for B, where the first occurrence of a red, a green, a blue, and a yellow is not necessarily 1, 2, 3, and 4. And what you'll find is that you have to create a map between the graph that you read in and the evolution rules that you have to produce, because you have to scramble up the numbers to make it work. You have to move the progenitors to the earliest numbers, which means all the other numbers got to shift around. So you use dictionaries to do it. Basically, you get from old mappings to new mappings as far as vertex numbers. And that, to show that, we can show that textually. Let's look at I'm going to get rid of this. The line numbers on the left side there represent node numbers. So this is vertex labels. This is vertex 1, vertex 2, vertex 3, so on and so forth. Okay. This is the first time and only time I see this color, so that's fine as 1. This is the first time that I see this color, so that's vertex 2. This is the first time I see this color, so this has to be vertex 3, and then this is the first time I see this color, so this is vertex 4. Then that would mean that maybe this is 5, this is 6, and how the rest map out, I don't know, but this seems to be one possibility. Or, let me see, how did I probably do it? Maybe I just, this would have been, maybe this becomes 12. Maybe I do straight swaps. This is 4, or excuse me, that would have been 7. This would be 12, and then this could be 5. You see these remain the same, 6, 8, 9. Whatever scheme you come up with, it doesn't matter. It's just that this one has to be 1, this one has to be 2, this one has to be 3, this one has to be 4. Or more generically, those 4 vertices have to be numbered 1 through 4, whatever order you do it in. So the reason that's a hassle is because your description down here, this is an edge between 1 and 2, where in your mapping, it's an edge between 1 and 2. All right, that isn't a good example. Here's an edge between 1 and, how about, let me find a 3. 315. And here, that's going to be 7. And presumably this is still 15 because it didn't need to change. 715, right? So you see you have a mapping where you have to change these numbers. when you're describing the evolution. So the dictionary is the data structure that's your friend on this to be able to map from the original numbers to the new numbers. Any other questions off right at the moment?